All right, let's talk about exciting electrons now. Exciting electrons, we can excite electrons using light, right? The electrons are charged, negatively charged particles, light. We have oscillating electric fields, which allows us to excite the electrons. So we're going to look at exciting electrons in metals first, and then exciting electrons in the sun. When we look at a piece of metal, like iron. If we have a chunk of iron, it's a solid. Iron conducts electricity, meaning that the electrons are loosely held in metals. And what did you learn about the bonding in metals? Did you learn about the electron C model? Does that ring a bell? The electron C model says that the nuclei and the core electrons are like pier pilings. So these are fixed. They'll vibrate because of temperature. But the electrons are pretty much free to roam. So the electrons would be like the ocean surrounding the pier pilings. There's nothing constraining it. And it's what we call delocalized. And so the nuclei are localized, and they're fixed in a certain position, able to vibrate. But the electrons are completely delocalized, meaning that they can go anywhere around here. And so here we have a sea of electrons surrounding the nuclei and core electrons. Nuclei and core electrons are going to give a net positive charge here. Core electrons are localized. The core electrons aren't what's conducting here, but whatever is on the exterior are. And when we expose this iron to light, it's going to excite the electrons. And so it depends on what type of light. If we expose this to radio waves, right? Radio waves, are they very high energy or low energy? Very low energy. And so electrons start off in what we call the ground state. You know what the ground state is? The ground state is the kind of the most stable state for the electron. So the electron starts off here in the ground state. What happens if we excite it? Well, this will be just an energy level diagram where we just plot energy here. Internal energy, enthalpy, whatever. And so we excite the electron with radio waves. They get just a little bit excited. And so they go to a higher energy state here. Are they going to stay in that higher energy state forever? No. What's going to happen is, they're going to drop back down. And so in this case, they'll absorb and they'll emit. That is, they'll absorb energy and emit energy. Well, what's the energy that they're going to emit? The energy that they're going to emit is the same energy that they absorb. If we excite it a little higher, we can get the electron a little higher, and a little higher, and a little higher. And eventually what we're going to do is we're going to continue exciting the electrons. So what I'm going to do is I'm just going to excite the electrons using not light, but just heat here in this spatula. And so I'm just going to grab my matches, but I'm using my matches for the pad stand, so let me place that here. Okay, so I'm going to use a flame to excite the electrons. And I have some stainless, which has a lot of iron in it. And so I'll start exciting the electrons here. Are the electrons getting excited? Yeah. And one thing is, there's some stuff on here. I don't know what it is. Oops, I got them too excited there. Did you see that? As you heat this up, hot metals can look exactly like cold metals, but if you feel around, you can feel the infrared radiation or the heat being given off. Right now I feel some infrared radiation being given off. That means what I have here is I've excited electrons up to infrared energies. And so they get excited here, and the electrons don't stay excited forever. Eventually they decay back down and emit infrared. And so this would be IR. Let's see. Radio waves are a bit more tricky. I'm not going to get into the radio waves. Okay, now if I can continue exciting, I'm going to get it excited through the whole range of infrared. Now, infrared just doesn't have one energy, it has a range of energies. At the highest infrared energy, we're at the highest infrared energy, what wavelength are we at about? 760. Actually, not 760, probably, well, we could say 760.1, if we're doing it by 10th. And just on the other side of 760. And then once I go beyond that, take a look at what happens to the color of this. Do you see it starting to glow red? Why is it glowing red? This is glowing red because, I've excited the electron now up to the visible. And so if I excite this electron a little higher in energy, it gets to the visible, and then when it drops down, it's going to emit red light. And then as I continue exciting this, it's going to go from red to orange. And then it's going to start adding those colors, and eventually when all the colors of the rainbow are being emitted, it's going to glow white hot. White hot means, there's electrons that are emitting red, and then a little higher, electrons emitting orange. What comes after orange? Electrons emitting yellow, green, blue, indigo, violet. When I have electrons, and there are a lot of electrons in metal, when I have electrons being all excited all the way to violet, then I get all the colors of the rainbow. And all the colors of the rainbow combined are going to give me white light. I don't have to use a flame to excite the electrons. There are other ways of exciting the electrons. Another way of exciting the electrons is by using electricity. And so we'll do that here. Let me show you. Got it. I don't want to do that. I'm going to flip off the lights here. Okay, so I'm starting to excite the electrons. Do you see any light coming off? No, but you know what? It should be. Actually, I need to flip this on. Let me flip that on. Okay, you don't see any light, but it's getting hot. And it's getting hot because we're exciting the electrons to infrared energies. Right? And they don't stay infrared forever. They're going to drop back down, and they're going to start emitting heat. And so we should start feeling heat around here. It's warm. Right? Okay, as I continue exciting the electrons, then, do you see that faint glow? Can you see that? Faint red glow? There's some kind of loose connection in here. Oh, there it is. This wasn't screwed all the way. A faint red glow, yes? And then orange, then more yellow. You don't really see the green, blue, indigo because all those colors are adding up. And eventually, we should make white light. Okay, so let's take a look at the colors of the rainbow with the handheld spectroscope here. And so just grab the this thing. And what you want to do is, do you see the square hole? you want to point the square hole at the light source. If you point the square hole at the light source, then hopefully you'll see the spectrum. You can move it back and forth until you get the brightest. But can you see the colors of the rainbow? Right. Well, let me turn it down, although the intensity is going to go down, but you're going to see a little change or shift in intensity of this. And so this is at max here. I'm going to turn down. And what you should see is a shift in intensity. You might not, because we're not close enough. A lot of you aren't close enough. You're probably getting a lot of background light. Do you see that? This is probably too dim to see. You got to be right up against it. Well, if I go right up against it, what do I see? I see a lot of red. Well, actually, I see a lot of colors. Okay, but we see all the colors of the rainbow, right? And so this is what we call black body radiation. You know what a black body is? Black objects, do you know what black objects do? Black objects absorb all colors and emit all colors of light. You know, and so like black things absorb all colors of visible light, whereas white objects, do you know what white objects do? White objects that was at 140 volts. Let me see at 120 volts. It's all right. So black things absorb all colors and emit all colors. So black bodies should show the entire rainbow of colors once those electrons get excited enough. And so one of the biggest black bodies around would be the sun. And so the sun, what we have is, the sun consists of something called a plasma. A plasma is the fourth state of matter. A flame is a plasma. And in the plasma, there's so much kinetic energy that when the atoms collide, the electrons get knocked off. And so what we see are gases that consist of ions rather than gases that consist of neutral atoms or molecules. And so plasmas are gaseous ions. And these gaseous ions, there's free electrons roaming around because, you know, there's so much kinetic energy, it keeps knocking electrons off matter. And those free electrons can get excited. And so if you take this out, we could see the solar spectrum of the sun, you know. You don't want to look at the sun directly, but if you look at it through this, we should. Is it sunny today? Do you guys want to see the solar spectrum and compare it to this? Okay, then why don't you go outside and take a look at the solar spectrum with this.